look at sample test 4. See how far we can get here. Number 1A. The maximum speed of a simple harmonic mass spring system with a spring constant of 500 newtons per meter, so that's telling us K, and a mass of 10 kilograms when the mass is displaced by 0.3 meters to start the oscillation. So what is Vmax? So we have a formula. We could go back to energy, but we can go ahead and use the formula. Vmax is A times the square root of K over M. K over M for the mass spring system is kind of the defining constant, just like for the pendulum it's G over L. And let's see, we have the mass is displaced to start the oscillations. We're assuming that's the maximum displacement, so that's going to be A. We got M, so we got everything. So we're going to have 0.30 meters, and then the square root of K, 500 newtons per meter, divided by M, 10 kilograms. So everything's in its standard units. So we can plug things in. 0.3 square root 500 divided by 10. Come on. There we go. 2.1213. Let's just go with 2.12 meters per second. Okay. Looking at part B, the period of a giant pendulum in simple harmonic motion that is 5 meters long on Earth. So the on Earth seems like a weird thing, but that's just telling us that G 9.81 meters per second squared. And we got the L for the pendulum is given there as 5 meters. And so depending on which equation you have, you kind of like to remember omega is G over L. It's also K over M if we have the spring there. And that is 2 pi F, which is 2 pi 1 over T. So that means that T, we asked for the period, so that's how long it takes for one oscillation, that's T. Rearranging this 2 pi 2 pi over square root of G over L will work. So 2 pi over square root of 9.81 meters per second squared divided by L needs to be in standard meters. Yes, 5 meters. All right. Square root of G. I think you got everything right. No. Don't know how we got that in there. We just want 2 pi. Okay. Our previous answer got in there somehow. All right, looks like 4.486. So that's going to be in seconds. So for the official answer, we'll just keep 3 sig figs. I think we've talked about this before, but on the test and so forth, I'm going to just go ahead and keeping 3 sig figs for whatever problem you have. I'm not very particular about putting 0.00 to give you the right number of sig figs, so we can just go with 3. And you're good. Don't give me 5. I might take points off. All right. Part C. The amplitude of a simple harmonic motion, 0.25 meter long pendulum swing, if its maximum speed is 2 meters per second. So we're looking for A. The line is kind of in the wrong place. So again, we can use our max speed equation here. So Vmax comes from the energy equations and so forth, but in this case, though, it's a pendulum, and so instead of K over M, we have G over L. We want the amplitude, and so let's rearrange this to get A by itself, and so A is going to be divided through by this square root stuff, so Vmax over square root of G over L, and so Vmax is 2 meters per second. G is same old G, and L 0.25 meters. All right, units look good, so 2 divided by square root 9.81 divided by 0.25. 0.3193. Yeah, so 0.319. A is a displacement, it's a distance, so meters. All right, looks good. Let's see, part D. The frequency of a sound wave with wavelength 4 meters, so that wavelength is lambda, traveling in air, so we've got speed of sound in air, so that's going to be V. It's 330 meters per second. So just have to pull out the right equation. So when we're talking about waves, a wave equation we were given on our equation sheet is V equals F lambda. And so we're looking for F, so just rearrange V over lambda. We got both of those, 330 meters per second over lambda, 4 meters. So F, 330 divided by 4. 82.5. And so if you look at the units, the meters cancel, and it ends up with 1 over seconds, and that's what hertz is per second, cycles per second. So 82.5 hertz is good. Yes. Part E. The tension needed to make a guitar string play an 88 hertz note if the mass of the string is 2 grams and it is 1 meter long. Assume the vibrating part of the string is 0.7 meters long. All right, so this first information we have an equation for the velocity of a string is square root of the force of tension over the mass per unit length. All right, and so we are asked for the tension. So we're asked for f of t. We're given the frequency of the note. All right. We're given grams and meters, so we're given information for mass per unit length. We don't have any information about the velocity. Okay. So we're going to need to, well, and we're given information here about the vibrating part, so that's what we're going to call L, the length of the string, the part that's vibrating. And so remember from our discussions in class that strings will have a fundamental frequency and then harmonics. So we'll just assume it's looking for the fundamental frequency, and so we can find that, relate that to the wavelength. There we have an equation for the fundamental frequency. And so where to put it? So F, the frequency of the fundamental, which we want to be 88 hertz, is equal to velocity of the string, which we have another equation for, over 2 times the length of the string. All right, so we said the string can vibrate at half a wavelength, and so that's where this comes from. And so let's solve for velocity here. So velocity then is 2L times the frequency we want, and so that's 2 times 0.7 meters times the frequency, 88 hertz. So that's meters per second. So that's going to work out. So 2 times 0.7, 88, 123.2 meters per second is the velocity of the string, the vibrations of the string. This is not the speed of the sound in air. This is the speed of the string vibrating. Okay, and so now we're still not there. This is kind of a complicated little problem. We want the tension, F of t. So let's rearrange this, square both sides, so we'll get V string squared and then multiply through by this. So we're going to have F of tension equals M over L times V string, that's string, squared. Okay, so M over L, 2 grams per meter, so that's we want everything in standard units, so 0.002 kilograms per meter. And then V we just got is 123.2 meters per second squared. 002 times 123.2 squared. 30.36. This is a force, so it should be newtons. Everything is in good units, yes. So let's say 30.4 newtons. Alrighty, he's kind of getting off the page, off the screen there. Hopefully it's okay. Part F. How many miles away is a lightning strike when its sound takes 8 seconds longer than the light to reach you? Assume the light gets to you instantaneously. 1 mile is 1609 meters and speed of sound is 330. Alright, so distance is just velocity times time. And we want the distance in miles, but let's go ahead and calculate it in meters first. And so velocity is 330 meters per second, and then the time is 8 seconds. The seconds are going to cancel out. It's going to be meters, so 330 times 8, 2640 meters. But we want it in miles, and so 2640 meters times 1609 meters, make a fraction that equals 1 per 1 mile. And so the meters will cancel and we get miles, so 2640 divided by 1609. .641. So 1.6, and that's miles. 1.64 miles. Right, makes sense. We had said that it was about 5 seconds per mile, so it's a little more than a mile. Well, a little more than a mile and a half. Okay, here we go. Part G, find the intensity in dB of a sound wave with this kind of watts per meter squared. So this is the power value, this is the intensity value. Watts is power. And so we got power per square meter. We have our formula for decibels is beta is 10 log intensity over I naught. I naught would be a good number to have on your sheet, or you can ask me during the test. But I naught is the threshold of hearing, the smallest sound that, I'm not sure if it's average or anyway, it's the basic level of hearing. So I naught is a given number, and it's 10 to the negative 12 watts per square meter. All right, and so we'll just plug in. So our beta here is going to be 10 log of 0.05 over 10 to the negative 12. Both of them are watts per square meter, so that's good. So we're going to write 10 times log to base 10 of 0.05 divided by 1e negative 12. Okay, looks like 107 dB, decibels. Okay, that's a 7. All right, part H. The time it takes a wave pulse to travel 0.5 meters in a spider web made of 0.2 gram per meter material. So this is one of those tensions in gram per meter kind of things with the tension of this. Okay, so this is FT. This is M over L in grams instead of kilograms. So we're going to use the formula velocity equals square root force of tension over mass per unit length, right? And so we've got the force of tension, 0.44 newtons, good unit, and then mass per unit length we want in kilograms, so we're going to say 0.0002 kilograms per meter Alright, so we can plug in and get velocity. Whoops. Square root of 0.44 divided by 0.0002. 46.90 meters per second. But we want the time it takes. So we're back to distance equals velocity times time. So time equals distance over velocity. Distance 0.5 meters. Velocity 46.9 meters per second. So meters cancel out. 46.9 meters per second. Okay. And so 0.5 divided by 46.90. 10.66 meters. Yes. No, seconds. Seconds. All right, 10.7 seconds. Okay, number 2. Find the number of atoms in 5 grams of aluminum. N equals what? Okay, so we need to get the number of atoms. We're going to take the mass divided by the molar mass, which is how many atoms per mole. I mean, how much mass per atom. Okay, and so yes, okay. So we do need to know the atomic mass of aluminum. So find a periodic table somewhere. Ask Google. 26.98 grams per mole. All right, and so we want to get the total number here. So we got 5, and since we've got both of them are grams, we don't have to convert to kilograms necessarily. 26.98 grams per mole. Oops, I'm doing the wrong. Okay. Right now I'm calculating N. What am I trying to do here? Well, let's go ahead and get the number of moles first, and then we'll get the number of atoms. All right, so let's do that. So the grams are going to cancel, and we're going to have moles. So we're going to 1 over moles, so the answer is going to be moles. So we're going to do 5 divided by 26.98. We get 0.1853 moles. That's N. And now little n, what we want is capital N, is the number of moles times Avogadro's number, which is the number of atoms per mole, right? And so we've got 0.1853 mole times 6.022 10 to the 23. I remember that right? Yes. Atoms per mole. Now the moles cancel out, and we're left with how many atoms we've got. A lot of those as well. 111.6 times 10 to the 21 atoms. 112 times 10 to the 21 atoms. Okay. Good. Temperature in degrees Celsius of a -10 degree Fahrenheit sample. So we need our formula. Temperature in Celsius is 5/9. Yes, 5/9. Temperature in Fahrenheit -32 degrees. So just plugging the stuff in. 5/9. Fahrenheit temperature is -10, -32 more, 2, and what do we get? 5 times, being lazy here, negative, or just put it in, negative 42, and then divided by 9. Come on. Negative 23.33 degrees Celsius. That's what we're looking for. I don't know why I got negative 23.9 before, but anyway, negative 23.3 degrees C. All right, let's do the next one. We're looking at going to Kelvin now from Fahrenheit. So let's go to Celsius first and then go to Kelvin. So we've got TF minus 32. So that's 5/9. Yep. 100 minus 32. So about 68. 5 times 68 divided by 9. 37.778. And then to get Kelvin, we just take the Celsius and add 273.15. .93. All right, and so we'll just go with 311 kelvins. A lot of degrees anyway. All right, let's keep on moving. Letter D. Find the average kinetic energy of air molecules, Simpson ideal gas, at 27 degrees Celsius. And so we want KE average, which is of the each kind of individual molecule's average kinetic energy for one molecule. So it's a small number, 3/2 kT. T needs to be in Kelvin though, so T in Kelvin is 273.15 plus T in Celsius, and 273.15 plus 27, 300.15 Ks. So we got 3/2. Boltzmann constant K here, 1.381, 10 to negative 23, I think. Yes. Joules per Kelvin, and then 300.15 kelvins. Okay, 1.5 times 1.3 times 300.15. Okay, 6.218 negative 21 joules. 6.22 and so negative 21 joules. Oh, now what happened? All right, I think that's the right number, but it's different than what I had on the other tests, so beware. On the earlier version I gave you had an error, it looks like. Okay, continuing on. The RMS speed of an O2 molecule at 27 Celsius. All right, so we've got VRMS formula. Remember, this is the kind of an average speed, root mean square speed, but it's the speed of one molecule. Square root of 3RT over MA is one equation that works. And let's see what we've got. We got 3. We've got R is 8.314 joules per mole Kelvin. Yes. And the temperature 27C, we just had that before, 300.15. Maybe keeping a few too many sig digs, but well, in the process of calculating, that's not a big deal. And then molar mass of oxygen, 1 is 16, so we've got 32 grams per mole, so 32 grams is 0.032 kilograms per mole. Alright, so now I think we've got everything in our standard units. Looks good. Kelvin is going to cancel, moles are going to cancel. Alright, and joules is, anyway, it looks like we're standard units, so we should be in good shape. So we got square root of.
This one here.